Okay, so yeah, welcome back. Um, so what I want to do for the rest of the time, I suspect we'll get through all of it, but I want to see. Um, what we'll talk about next is going to use the machinery we just went through. In particular, it's gonna focus on this idea of being able to capture there exactly being one, right? So we're going to capture the idea of there as exactly one F. And we're going to use that to give us another way to pick out single objects. So remember when we were first introducing FOL, all of this Halcyon days of last week, right? I talked to you about how there's broadly two types of singular terms, right? There are names and there are definite descriptions. So names functioned by just sort of picking things out, right? We don't necessarily learn anything about what an object's like by learning that it's picked out by a name. In contrast, definite descriptions pick out an object via a description that one and only one object satisfies, right? So a cheap one, the Californian logician that works in Tilburg University, I'm pretty sure that picks out me. There might be other things, but I'm pretty sure that's me. So a definite description is a description that exactly one thing occupies. That should already set off ideas of where we're going next, right? Contrast that with an indefinite description. An indefinite description doesn't pick out a unique object. That could be because there's more than one thing that satisfies it, or it could be because nothing satisfies it. Right? So a philosopher or a person who studies at Tilburg University. So how are we going to symbolize definite descriptions in first order logic? Well, kind of gave the game away a second ago, right? This is where we get old Bertie Russell. So Bertrand Russell offered an analysis of definite descriptions. And his analysis was actually meant to be of the word the. So he was originally trying to offer an analysis of every occurrence of the English the. He did not succeed there. But at least when it comes to offering definite descriptions, he's got a pretty good story. So Russell's idea is that the F denotes the one and only one thing that is F, where F could be any predicate we like. Right? That is, if we hear the F, it entails that there's at least one and at most one thing that is F. And then if we wanted to say something like the F is G, well, that's going to be true if and only if there's at least one thing that's F, there's at most one thing that's F, and every F is G. So we're going to take this analysis and we can use it to give us a way to capture definite descriptions in first order logic. So here's the Russellian analysis. We can say that the F is G if and only if there's at least one F, right? So existential X Fx, just like we talked about a few minutes ago. There's at most one F, that is, for all things, if it's an F, then it's identical to our first one. And whatever it is we're talking about, it's also a G. So this gives us how to express the F is G. We've got the existential in the front attached to whatever predicate we're talking about, conjunction, and then a universal with this conditional to tell us whatever it is, it's identical to our X. And then finally, that our X is also a G. Again, whatever G predicate happens to be, right? So the Californian logician works at Tilburg, right? The predicates would be is from California and is a logician. This would be everything that's Californian and a logician. And this could be works at Tilburg. Again, you can kind of see how this goes, right? The tallest person in the room is registered for the logic class. T could be the predicate here, and then this could be R, right? There's at least one thing that's the tallest person in the room. There's at most one thing that's the tallest person in the room, and that person is registered for the logic class. This structure is wonderful. We can use it in so many different ways. So this is a handy way to start thinking about exactly one. Because exactly one, we can also just express as the, with a definite article in English, right? So we can give some practice. Right? Here's our symbolization key. Our domain can be universal. We can have little d for Dwayne, little m for Miami. W is a wrestler. S is a premier sports entertainer. And L is a two-place predicate with lives in. Right? So if we were just going to symbolize the wrestler, right, how would we do the wrestler? Right? So if it's the wrestler, how many are there? At least one, and at most one, right? So there's at least one and at most one thing that's a wrestler. So we can say there is something, it's a wrestler, and for all y, if it's a wrestler, then it's identical to x. Right? This is using the f that we just talked about in the previous slide. Right? Okay. Now, how would I say Dwayne is the wrestler? Right? How would we say Dwayne's the wrestler? Yeah. Well, we don't, so I get it. That would tell us that the wrestler and Dwayne is a wrestler. So we can do this actually a little bit more directly. So we want to add, we can take what we have, and we want to add another conjunct, but what's our next conjunct want to say? Maybe one way we can, yeah. Identity. We can use identity here, right? Our last bit can say x equals d, right? So, again, we can paraphrase this as the wrestler is identical to Dwayne. There's at least one thing that's a wrestler. There's at most one thing that's a wrestler. And the one and only one thing that's a wrestler is Dwayne. So there is something that's a W. For all y, if y is a W, then it's identical to x. And that x is Dwayne. Yes?
Make the first example for the wrestler. You explain like where the universal, or like in English, like what the universal y means and like what that y variable stands for.
Yes. So this is saying, right? Again, the easy way to think about it is this first clause is telling us there's at least one thing that's a wrestler. And then the second one is saying for anything in the domain, if it's a wrestler, it's identical to our first object. So basically, this is a way to say there's at most one.
And like, how do you spot, like, looking, like, just having given that English language, like, if you see that, like, how do you spot that you're going to need two variables?
Good. So importantly, one thing we can help ourselves out is if you see the, right, you're going to have to say there's at least one and at most one. Right? Because again, what does the say? To go back a couple slides, if we take Russell to be right, the F tells us there's at least one F and at most one F. Right? So we can read the F as at least one, conjunction at most one. And that's what this is encoding. At least one, at most one. It is literally using that symbolization we did just a few minutes ago for the at most and just sticking them together with the at least. Yeah, that's the nice thing about it, right? So, okay, good. We got the top one. We got Dwayne is the wrestler, right? This basically just, we have that unpack the wrestler, and then we have a conjunction that tells us, and it's identical to the name we have. How about the wrestler lives in Miami? How would we do the wrestler lives in Miami? Oh, don't everybody look so happy. Right? Yes.
Can we copy the first thing?
Yep.
And then use that as one in L.
Yeah, exactly. We take the top one, we add a conjunction that says LXM, right? That X lives in Miami. Whatever the X is, well, that thing lives in Miami. And hey, what is it? Well, it's a wrestler, and everything that is a wrestler is identical to it. It is the one and only. Cool. Okay, with me so far? Again, we're moving at a pretty good clip, but I think we're getting it. So our last one, the wrestler is the premier sports entertainer. Right? This one's a little bit harder. Right? So one thing we can help ourselves out here is, right, how many different at least ones are we going to have? And how many different at most ones are we going to have? 2 of each, right? Because we have the wrestler, so there's at least one and at most one wrestler, and then there's also at least one and at most one premier sports entertainer. Does everyone see that before we go on? Do we get that, right? So we can take the wrestler, and we can take the premier sports entertainer, right? Which is going to have the same structure, just instead of W, it's going to have S. And now we want to say that they are what? What do we want to say about the 2? They are the same thing, right? And how do we say they're the same thing? What's our tool for saying that? Identity, right? Identity, the equal sign. So we're going to have 2 existentials in the front, because we want to say there's exactly one wrestler and there's exactly one sports entertainer. And then the end of our sentence is going to be these 2 variables are identical. So we can say there's exactly one wrestler X, there's exactly one sports entertainer Y, and X is Y. Or in our formula, like so. This tells us there is something, it's a wrestler, and for all Z, if Z's a wrestler, then it's identical to X. And there is some Y, such that Y is a premier sports entertainer. And for any Z, if Z's a sports entertainer, then it's identical to Y. And finally, our last bit, we've been talking about the same thing the whole time. And this could go on. If we had the wrestler is the premier sports entertainer and is also the person who lives in Miami. You could see how this goes. It'd be a little bit harder because we don't have person, but we could build that in. Again, this is the kind of thing that we can extend indefinitely if we want to. But what's important is that we know how to build these sorts of definite descriptions where we ascribe properties. Okay. Before we press on, we'll pause, ask, what questions do you have for me on this machinery? Don't stress if it's not clicking yet. As you can expect, we're going to do a hell of a lot of this in the tutorials. Yay! So many symbolization exercises. It's so much fun. Yes?
Could you move the for all Z in the front here too, and then omit both of them?
Yes, so you can put this in the front and it's perfectly fine, and have both of them be under the same range of quantification. That's totally fine. The reason that works is because this inside the big brackets is still just a conjunction. And in order for this sentence inside the brackets on all the way out to be true, you got to make all the conjuncts true. So the order of the quantifiers here does not matter. Right? And if they're just scoped over one conjunct, or if they're over the whole damn thing, that doesn't matter either. Good. Okay. So this sort of definite description machinery is one of the lovely, lovely little upshots of FOL with identity. Because to drop into doing some philosophy of language for a second, one thought we might have is that when we think about proper names in natural languages, they don't actually function like proper names as I described them earlier. They always convey at least a little bit of descriptive capacity. And that actually, this is really how we should understand every natural language proper name. There was a long-running philosophical project to do this. Just between friends, it didn't work, right? But this was a huge effort in the first half of the previous century to try and understand all natural language references in terms of this definite description machinery. It was very worthwhile in a certain sense, because what it suggests is that maybe we could build a notion of reference entirely out of qualitative descriptions, which is handy. Right? If you say, want to pick things out of a database without just giving them names, you maybe could just build definite descriptions and have them pick out your objects. Something to think about. Okay. So one other really neat upshot of this machinery is that we avoid something kind of weird. So take sentence 1, the present king of France is bald. And sentence 2, the present king of France is not bald. Well, given that there are no French monarchs, rather infamously, anymore, right, it looks like neither 1 nor 2 are true. If we round up the bald men, right, then the present king of France is not going to be there. Similarly, if we round up all the hirsute men, that is, the non-bald ones, he ain't going to be there either. So it looks like 1 and 2 are both false. But this is a problem, right? Because this seems to run into an earlier assumption we made about no gaps, no gluts. How could both of these be false? Because it seems like if 1 is false, then 2 should be true. And if 2 is false, then 1 should be true. So that's a weird problem. Again, slightly weird. Russell gives us a way to solve this. And the solution is actually pretty ingenious. And it has to do with the scope of this not. Sentence 2 is ambiguous. Sentence 2 is ambiguous between a version where the not just attaches to the bald and a version where it attaches all the way in the front. That is, we can hear it if we think about how to symbolize these 3. So how would we do the present king of France is bald using this key? So we'd say there's at least 1 present king of France, there's at most 1 present king of France, and that thing is bald, right? That is, there is something that's a k for all y, it ky, then it's identical to x, and x is b. Cool? And how would I say the present king of France is not bald, where we just read this as attaching to the baldness predicate? How would I say the present king of France is not bald? Yeah, basically just this sentence with a negation right there, right? With me so far? Now, last one, how would I say it's not the case that the present king of France is bald? Yeah, basically we're going to take this and we're going to kick it all the way up in the front, right? So we get this. Now, when we look at these 3 sentences, right, does the falsity of 1 imply the truth of 2? Does the fact that there isn't exactly 1 present king of France that's bald mean there's exactly 1 present king of France that's not bald? No, right? Because there might just not be any such K. But in fact, that would explain why 3 is true, right? That would explain why 3 is true. So the problem that earlier we mentioned, literally the previous slide, about the apparent contradiction between 1 and 2 both being false, had to do with not understanding their logical structure. If we actually spell them out in FOL, you can see the difference. One of them, you have the scope just on the negation, or on the little last predicate here. The other way to read it, it's got the wide scope. And there's no problem with 1 being false, implying 3 is true. Because 3 doesn't mean there's any present king of France. So if we're careful with how we do our symbolizing, we can still maintain the idea of no gaps and no gluts. So this is a little housekeeping. It's nice housekeeping. It's good. It means that we can still maintain our assumptions that we started off with. Okay. So we've done at least, we've done at most, we've done exactly, and covertly, we also did the. All we got left to do is talk about defining FOL sentences. Right? So I want to start on this, and we'll get through as much of it as we can before we finish up for today. This is going to be a little bit messier than when we defined them for TFL. And the way we're going to do it first is we're actually going to define a kind of proto-sentence. We're going to define something called a formula. And then we're going to say when formulas can become or are sentences. So it's going to be a two-step process. So first things first. We talked earlier, in fact, one of the very first things we had for FOL, I told you there's 6 kind of symbols. Much like with TFL, we can say that an expression of FOL is any concatenation of these. Don't care about the order, right? So it's just like we had before with an expression of TFL, right? But much like before, not all expressions are going to be sentences. So this is just to kind of get you in the FOL door. Now we'll say that a formula is any sentence or any expression that can be turned into a sentence by adding a quantifier. So this is our kind of proto definition of a sentence. It's our first step to get us there. And we can say a term is any name or variable. And an FOL atomic formula, well, I'll read it and then we'll go through it. If R is an n-place predicate, T1 through Tn are terms, then R, T1, Tn is an atomic formula. If T1 and T2 are terms, then T1 identity T2 is an atomic formula. Nothing else is an atomic formula. So, unpacking this, all this is saying is that our base is going to be a predicate and the relevant number of terms. If it's a 2-place predicate, then it's a predicate and 2 terms. If it's a 1-place predicate, it's the predicate and 1 term. And importantly, you can always put 2 terms on either side of the identity sign. This is our new base unit. Right? We talked about this last week. The base unit is a predicate, the relevant number of terms. Nothing else is going to count. So that's a formula. Now, how do we get to sentences? So to give you some sample atomic formula, nothing shocking here. Now I can give you a lovely, beautiful little 9-place, we'll call it a definition, where we characterize the notion of formula. Right? Every atomic formula is a formula. If you have a formula, you can add a negation in front. If you have A and B as formulas, then you can stick a conjunction with brackets. This looks a little familiar, doesn't it? Yeah. Basically, everything for the first 7 is the same. Just like for TFL, because it's telling us how to use the connectives, and we know how to do those. The same rules apply. The only difference is 7 and 8. Right? 7 tells us, right, if you have a formula that contains a variable x or y or z or whatever you want, and that isn't already associated with a quantifier, then you can stick a universal in front of it. Alternatively, if you have a formula and a variable in it and isn't already associated with a quantifier, then you can stick an existential in front of it. This is a little bit easier to unpack if we look at examples. But note, the rest of it, all the same. So clauses 7 and 8 encode the idea that if you've got a variable that isn't attached to a quantifier yet, you can still maintain a good formula if you slap a quantifier in front of it associated with that variable. So we could take this one, for example, bxx, and stick an existential in front of it, according to clause 8. Or we could stick a universal in front of it and still get a formula, according to clause 7. The important grammatical rule is that the variable needs to not be associated with a quantifier yet. Yeah? So for example, we cannot put existential x in front of this one, because x in the formula is already associated with the universal. But we could put universal y or universal x. Yeah? Again, we don't really care what it says. This is just thinking about the pure grammatical rules. These ones, though, are bad. And these ones are bad because we have clashes of variables, which are no-nos. Remember, we talked about this last week. Okay. So, we can then talk about the main logical operators and the scope of various operators in a formula. The main logical operator of a formula is the operator introduced last when it was constructed according to the rules. Again, just like what we did with TFL. And the same thing with scope. Scope is going to be, well, the formula that it's the main logical operator of. So these are just like they were before. So we have a rule now to build atomic formula, right? That was that clause definition, the 9-clause definition. Importantly, atomic formula aren't all sentences. Many of them are, many of them aren't. This one, for example, is a formula but not a sentence. All it's missing is the quantifier. That is, we can turn bxxx into a sentence by binding the variables, telling us how we're supposed to replace them. The quantifiers tell us what you're supposed to do with the associated variable. Without them, you don't know how to read the sentence. Right? This is just kind of like, once you have the associated variable, you know how you can replace things in the gaps. There's at least one thing that satisfies this 3-place predicate. Everything satisfies this 3-place predicate when you plug it in for all 3 places. It effectively tells us something like, what objects can we plug in? So, the last bit to get us to our definition of an FOL sentence, right, has to do with the variables. We can say that a bound variable is an occurrence of a variable within the scope of an associated quantifier, and a free variable is one that isn't bound. Right? So, for example, in this one here, the x is bound by the universal quantifier, right? It is attached to the quantifier. We know what we're supposed to do replacing the x. The y is free. And if we look at this one, it's tricky tricks, but if we look at this one, are there any free variables at our bottom sentence? Yeah, so if we look really carefully, this x here isn't bound by any quantifier, right? The scope of this is just the first bit. The scope of this is just that disjunct. There's no quantifier associated with that x. So that x is a free variable. We don't know what to do with it. Okay. So this is a weird kind of run-up, but finally, to tell you the definition of an FOL sentence, it's going to be a formula that has no free variables. So remember, a formula was one of the ones that satisfied our definition. To go back a few slides, that satisfied this. It's going to be predicates with the associated terms, could be filled in, could feature these various connectives in lots of the different ways, the ways that we've been told on how to do them, right? But importantly, an actual sentence is going to be a formula with no free variables. That is, every variable that's there is going to be bound by a quantifier. Yeah?
If you have like the e, that would be xxx,
Yes.
Then with the oh no, because I thought that it said like that BXXX wasn't a sentence.
So this by itself isn't a sentence, but as soon as we bind all these variables, we're good. Right? And importantly, we couldn't have these x's associated with different quantifiers because that would violate 7 and 8. Right? 7 and 8 basically guarantee that if you've got a string of variables like this and you slap a quantifier in front of it, it controls all of them. So again, our definition, finally, of an FOL sentence is any formula of FOL that contains no free variables. So it's a long run up to this, and that's because of the grammatical complexity. But the thing that's important for us to remember, and this is really the big thing, right? Again, the base unit where every FOL sentence starts is a predicate and terms. If you have a predicate and a name, cool, you're done. You've got a sentence. If you have a predicate and a variable, that variable has to be associated with a quantifier. If there is no attached quantifier, you have not got a sentence yet. You have a formula, a proto-sentence. Until there's a quantifier that binds that variable, you haven't said anything yet. You need to have an existential or universal attached to every given variable. Okay. Again, I know grammar's fun. Yay! But it's important that we get the grammar right when we're building the sentences, because otherwise the evaluation machinery doesn't work. So, okay, that's all fine and dandy. We now know how to do a bunch of symbolizing from English into FOL. We know how to capture things like at least, at most, and exactly. We know how to capture the, which becomes another way to say exactly. And we've walked through this really exciting bit of grammar defining the conception of an FOL sentence. What we haven't done yet is said when FOL sentences are true or false. Right? Now, if you remember with TFL, we had the beautiful truth table machinery. Unfortunately, for FOL, we cannot use tables, right? Which is a shame. Tables are amazing. Right? But tables only work when you have atomic sentences as the base. Right? Tables are built of valuations. We can't use that here because we don't really have atomic sentences. We have terms and predicates. So what we're going to talk about next week is the replacement machinery for evaluating FOL sentences. These are called interpretations. I would strongly recommend, please, I don't know if you've been reading the book as we go along. You probably should. It's really good. Tim's done a great job, right? Please strongly recommend that you read the chapter for next week on interpretations, because it might not necessarily make sense if people just come to the lecture without having gotten that stuff already. So that's what we're going to talk about next week. And that will be the last new stuff before the midterm. So thanks for coming, guys. Have a good time, and I will look forward to seeing you all in tutorials later this week.